All right. Hello to LinkedIn and YouTube, and welcome to our first live stream at Firebolt in a while. It's a pretty exciting and momentous occasion to be going live. And also, hello to everyone watching this after the fact as a video, because I imagine not a ton of people are hopping in as soon as the stream starts, but the intro will find someone. In any case, my name is Cole Bowden. I'm a developer advocate at Firebolt. I'm joined by Demian, one of the engineers who implemented geospatial functionality in Firebolt. We launched geospatial functions this week. We had a public preview going a couple months back, but this week is when they're officially live. We're proud to announce it's out there. There's documentation, there's a couple tutorials and demos you can go check out. And today we're going to go into a little more detail about how we implemented it, go through a little more demo that's interactive. If you have questions, you can ask them either in LinkedIn chat or in YouTube chat. But Demian, welcome to our first LinkedIn Live as well. How are you doing today?
Hi, Cole. Yeah, thank you. I'm doing great. It's really exciting that Geospatial Sport is finally out. I'm super excited to talk about it with you today.
So I think without further ado, we can just get into talking about it. And I think the first question and where we want to get started to discuss how we did geospatial support is exploring the differences between a geometry and a geography, because we made a choice to go with geography, but you need to understand what that means.
Yeah, exactly. So basically, in databases, there are these two types, geometry and geography. Some systems implement both, most implement one of them. And the difference is basically that geometry models everything as a flat plane. But as we all know, hopefully, Earth is in fact not flat. It is something like a ball, almost a ball. And that is what geography does. So geography models the coordinates that you give it as points on a ball, on a globe, different from geometry, which is just on a flat plane. And that plays a role, for example, when you want to calculate really huge distances, when you want to compute the distance between London and New York, then this really makes a difference because the distance is going to be quite a bit different. And it also matters for things like checking if when you have an area, a very big area, and a point somewhere near the border, the boundary of that area, the result whether that point is inside that area might be different depending on whether you use geometry or geography, where geography, if you're talking about this actually being on the Earth, is actually obviously the correct answer here.
Yeah, and I think one of the best ways to simplify this, if it's hard to grasp this, is like if you've ever seen a flight map going from, say, like New York City to Europe, like most maps we use are the geometry format where it's a projection of the Earth as if it were flat. And so you see what is a straight flight path look like this arc going up north and back down again, when in reality that's a straight line. And so if you're computing distance, you need to have the Earth curved so that that straight line is measuring the right distance. So that's a important thing to have for these kinds of things, and it's more precise and accurate. But it comes with some technical snags, right? It's easier to do geometry because if everything is flat, the math is quite simple. But because we went with geography, the math is not as simple. So, what are some of the snags that we've had in implementing geography?
Yes, so definitely the math gets more complicated when you do it on a ball. One thing you immediately have to consider is that a ball doesn't have an end. So when you have a format where you have a point on one end of the spectrum and like at coordinate 0, let's say, and let's say the other end is 1, then you can just easily calculate the distance here. But on Earth, when you have a point at coordinate at latitude minus 179 and one at plus 179, they're actually quite close together. So you have to take care of things like these when you're dealing with geometry on a globe, which we call geography. Yeah, and what we use for this is a library called S2 Geometry. It is a library developed by Google, and they open sourced it. And it really does a lot of the heavy lifting that is required to get actual correct results and robust implementations of these, well, primitive operations that you need to implement these things.
And then in the technical blog that we've written, which hopefully is linked as part of this, if not, you can go to the Firebolt website and check it out. You also talk in detail about snap rounding. Do you want to give a quick overview of what that is and why that is also a tricky thing to implement on geography?
Sure. So snap rounding, I think the blog post talking about snap rounding is not actually out yet.
Oh, it's not out yet. So another thing to look forward to.
Exactly. So it will be out soon. What snap rounding basically means is this is not particularly a geography versus geometry thing. It's more of a accurate thing of accurately representing numbers in the computer. So imagine you just have a straight line from A to B, and then you have a point somewhere in the middle. And now you have floating point numbers. If you like listen to any computer science lecture, you learned about floating point numbers and that they are not able to represent every number accurately because there are infinitely many numbers between 0 and 1. A computer can't represent all of them. So you will at some point run into the issue that you have a point that should be on that line, but the math doesn't quite work out, and it's actually ever so slightly next to the line, not on it. But we want to be able to handle that correctly, because what you meant is that that point is actually on that line. And so what snap rounding is a solution to that. And what snap rounding does is whenever 2 points are very close together, in the case of Firebolt, that's 1 micrometer, which is extremely small, then they are treated as the same. They are snapped together. That's where the name comes from. So we modify the line segment to actually go over this point that is 1 micrometer next to the line, technically.
So if you're trying to measure the distance between plant cells using geography on Firebolt, it might not work.
Yes. Probably not the right choice for that use case. You're right.
But yeah, so and how do we optimize that? It seems like having to check for such small distances could be a little complicated in the engine.
Yes, exactly. It is. And we avoid actually having to do that as much as possible. The most important optimization for that, what we use, is that we calculate so-called coverings of any object that you store in Firebolt. This covering is basically a rectangle. It's not a true rectangle because it's on a globe, but imagine it's something like a rectangle that fully encloses your object. And what you can then do, you can compare, are these rectangles even close to each other? And these checks are incredibly fast because these rectangles are represented by a single number, and you just do one comparison. Is this number larger than this? And then you know, no, they're not even close to each other. It's basically what it boils down to. And that is the first optimization that we do whenever we try to see if 2 objects are close to each other. And if that check already returns that they're far away from each other, we immediately bail out and do nothing else with it. And there are similar optimizations that also come into play when one object is actually deeply inside the other object. Then a similar optimization plays a role. Then we don't have these rectangles surrounding the object, but we have rectangles that are all completely within it. And then you can do a similar kind of optimization here.
And so it's only when we're looking at things that are close but near the borders of where they are that we have to start looking at exactly where these boundaries are and explore snap rounding to accommodate for floating point imprecision.
Exactly. We can actually have a look at it later when we look at our small demo, we can have a small look, like peek at what this looks like.
Yeah. Do you want to hop into that now?
Sure.
All right.
Let's
So
do
we'll
it.
pull the demo up on stage. So this has been built to explore how Firebolt does geography and visualize it for you. I've also heard a story. We built this demo in an interesting way, right?
That's right. So I am not a web developer. I know very little about JavaScript and setting up servers to respond to requests. This was actually almost entirely AI generated. So I assume no responsibility over any visual bugs, but they shouldn't be there. All right. So yeah, what we have here is a map, and we can draw some things on this map. It's all backed by a data set of accidents, traffic accidents in the US. So we're going to only have a look at US data because everywhere else will be empty. And one of the first examples I always like looking at, because I don't know, it's a place that everyone has heard about. It's the Central Park in New York. For example, here we can draw a polygon around Central Park. So now we have a polygon here. And now we can send a query to Firebolt that queries this entire data set of accidents. It's about 7 million accidents that are stored in there. All are associated with a start location. And we can check for any accidents that happened within the Central Park. Because as I understand, there are a couple of roads in here, actually.
Yeah, it's not that many, but they're there.
Well, but it's quite a few accidents, actually. So we can have a look at what actually happened here, because up here, this was automatically populated with the query that was sent to Firebolt. So what happened here is that we select the start locations, and we then transform them to a standard format called GeoJSON, which is what this map application that I'm using here speaks. We select that from the US accidents dataset, but we only select those points that are covered. That's using the first geospatial function that we're looking at here. It's called stcovers, and basically it takes two inputs and it checks whether the second input is inside of the first input. And here the first input is a GeoJSON representation of the Central Park, of this polygon that I just drew. And the second input is our start location. And then we can see that all of these points here are within the Central Park. And
it's worth maybe pointing out that the start location is in this data set where we're tracking traffic accidents.
exactly.
There's a start location and an end location for the accident, because sometimes they move. But this is just where they begin.
Yes, exactly. I'm just looking for start locations here. Some of the data also doesn't have end locations in this data set. I mean, sure, this is interesting. Down here, we can actually look at what the data looks like that is displayed here. So it's all these GeoJSON objects that all represent a point. But of course, this comes with everything you want a database to do. For example, you cannot just select the start location. You can also, I know there is a column for the severity of an accident. So we can also just query for that as well. And I programmed this to now color the different severities differently. And this way you can do all kinds of analysis that you want, right? You could now group this by year and see how many accidents happened in Central Park in each year, and then maybe generate some insights from that because that's correlated to some other change.
And of course, we could just go draw a different polygon somewhere else.
Of course.
I mean,
where do you want to draw a polygon?
let's just do Manhattan. You're hovering over it right now. Let's see if it's better or worse. There's more density of roads, so
let's see. There's I don't know anything about this. There is a big square of roads here. So let's draw a polygon around that, and let's see what accidents happened here. Okay, not so much on the inside. This is near Washington Square Arch. So not that many accidents happening here, actually.
Yeah, and I bet you I think it's because the roads that go through Central Park tend to go pretty quick, whereas here it's lots of start and stop. So you're not going to have as many cars going quickly, which will mitigate the risk of collisions. So, and you could zoom out and do somewhere else in the US. We don't need to do that, but it is a map. It is a fully functional data set that works here. You can actually, if you want to mess around with this, you can download this data set. We're hosting it as a sample data set in an S3 bucket. We have some demos that allow you to do something similar to this, but so it's out there. If you want to fiddle around, that is a thing you can do.
I think in the blog post that we published yesterday, there's actually a link to a GitHub repository where TJ, someone else from the company, our content guy, created a nice demo for that, where you can just try out these queries.
Yeah, and you can ingest the data. There's some different strategies for that, and you can see how it works in Firebolt itself.
Yes. So I just zoomed to another example. I was told this is an interesting example. So what we can also do, now we've seen points and we've seen polygons, and there is one third kind of shape that you can have in the geography format, that is the line string. So let's see what line strings can do. For example, we can try and see how many accidents happened along this road. I was told to use this road. Apparently, there are a lot of accidents here, so let's use it.
Yeah, the I-90 corridor is notorious.
So let's try and draw a line string that hopefully roughly follows this road. So I think this should be fine, right? So now we have a line string here. And I have a query here which will select anything that is within 10 meters of that line string. Okay, and let's see what query it generated here, and then look at the result. So basically what we're doing here is, again, we are selecting all the start locations, convert them to GeoJSON. And this time we are calculating the distance from, this time, a line string that we just drew here, and that was converted to GeoJSON. We calculate the distance between that and the start location of the accident and compare it to 10, because SC distance returns the distance in meters. So we're returning anything that's less than 10 meters. For any US folks, I hope, Cole, can you tell me how much 10 meters is in yards?
It's like about 30 feet. I mean, give or take a little bit is my understanding.
All right. Yeah, so, and then we see, yes, like you're right, there are lots of incidents on this road. We can actually do the same here, also select severity, so we can see how severe the accidents actually are. And let's also order by severity, because I know then the colors are going to be nice that we show here. Right, so, and then we see, okay, so this is, all the red dots are severity 2. These seem to be, actually there are also a bunch of severity 3 ones, all these blue ones here. And what's yellow? Even severity 4. So lots of accidents, especially around this area, interestingly. I guess they're, all right, this is where you enter or exit it. So yeah, lots of incidents happening here.
Yeah, and it's a bridge on a high-speed highway with some interchanges and tight turns, so it makes sense that you would see a lot of collisions, and also they'd be more severe due to the high speeds relative to Central Park. So the data set makes sense, and visualizing it with the line tool is actually very cool. So you could, draw a polygon that looks like a very long snake if you wanted to. What are the advantages of using like this line string as opposed to a polygon?
Well, you could definitely do the same thing with a line string, with a polygon. Sorry. but it is in this case the more natural way of representing it, basically. You could also imagine this coming from the line a car took. You record locations where you tracked a car, and then you connect them by a line. And obviously, there is no polygon to draw here. The car moved from one location to the next one. You could connect them by a line, and that's what you would use line strings for. Yeah. Actually, I do have an example where we combine this with a polygon, because when we look at this query, we actually see that it will have to calculate the distance between this line string and any accident that happened in this data set, and will then check if that's less than 10. But that's not nice. That actually takes a bit of time. And we already talked earlier about how we can optimize checking whether a point is inside a polygon. If you remember using these coverings where we check if it's far outside or far inside the polygon, and then optimize using that. And I've basically manually implemented something similar here. We can later also look into how this is also possible to do automatically. But if we now draw this line string again, because I believe I built this web app so you can't reuse it. So let's just draw it again really quickly. And now let's run the same query again, but this time we also draw a rectangle that roughly outlines this line string and everything that is within 10 meters. I basically just took the smallest latitude and the largest latitude, subtracted or added 10 meters to it, and that's the boundaries of my polygon in latitude, and in longitude the same thing. And this is what that would then look like. We intersect, that's another geospatial function. We can intersect this polygon with the start location. And then we know, okay, it is at least within that polygon. And only then we calculate the distance between the line string and the start location, compare that to 10, and only return the points that are within 10 meters of the line string.
And so the benefit of this is that when we're calculating whether or not it's inside the polygon, we're able to very, very quickly exclude rather, the rest of the universe that does not exist inside this polygon.
Exactly. And we can also have a look at what this looks like. So if we just trace this polygon that the query automatically generated, I have a small trick here to actually visualize these coverings that we compute internally. So if I turn this on, it gets a bit larger, but this is basically it. So this is what we will see internally. There is this one, sorry for zooming, it's a bit hard on a laptop. We have this one pretty big box, and then there are 3 smaller boxes, which are required to also cover the rightmost side of the polygon that I drew. And each of these boxes is basically just represented by one integer, like one number. And whenever we look at the point that's maybe over here, we will very quickly see that it does not intersect with these boxes, and we will just not look at it any further. And this check is much faster than actually calculating the precise distance between the line string and the point, which needs a lot of calculations to actually get the precise distance in meters.
And so writing queries like this, it's with Firebolt, the goal is to have things be highly performant, low latency, interactive. And with a larger data set, this is an optimization that ensures that you can maintain that speed, even if you have a long line string. And I mean, this data set has 7 million rows, I think, or around that much. If you have, 10 billion rows, then this would be a pretty big deal.
Exactly. And yeah, I mean, what's also something that is coming up is actually a first version of spatial data pruning. It's not out now, so when you try geography in Firebolt today, you won't see it yet, but it's soon going to be there. And what we will do then is we will actually compute a covering of our line string. So let me just run some other query to get rid of this drawing. It's a bit confusing. So if we then draw this again, I think I have to disable this. Okay, let me draw this again, maybe a bit less detailed. Okay, so like this. And we can also calculate such a covering for this line string. And what Firebolt will do is it will check if this covering, so these 4 boxes, or in reality, it will actually use more than 4 boxes. Let's say if we use 128 boxes, I think I have to check and uncheck this. Now you can barely see it from the zoom level, but down here, there are these boxes. And we will actually intersect this with also a set of boxes that represent an entire tablet in Firebolt. And a tablet is basically the file structure that Firebolt stores its data in. So when we then see this file does not include a single point that could even be near this line string, we will completely skip the entire tablet, the entire file. And that actually speeds things up a lot.
Yeah, and so instead of excluding from a polygon, you can exclude from storage in the database itself, right? Which is even more efficient. That's faster even than the manual optimization.
Exactly, because the optimization we talked about before, it was per object. So for every object, we do a very quick check first, and then decide if we need to do some more accurate calculations. But this time, it's for an entire part of your data. So could be, depending on the size of your data, millions of rows at once that we skip.
Yeah, and instead of reading, most or all of the data, with a selective query, you could avoid reading 95% or 98% or 99% of the data. And the less data you read, the faster you get query results. That's kind of an inherent part of optimizing Firebolt. That's our strategy a lot of the time, is read as little data as possible to get things much faster.
Exactly.
That's interesting. Do you have a rough idea of when we can expect that to be live?
Oh, now you're putting me on the spot.
Oh, I mean, I'm just asking for, is it weeks, months, years?
It should be weeks. So the first version that does this on a tablet level should be out within weeks.
Okay. And keep an eye on release notes, the release roundups. We'll communicate it when that happens, if this is something you want to test for yourself. This is maybe an exercise for our viewers, as if you're watching this in live or shortly after it goes out. You can go use some functions with line strings and come back in weeks and see how much better it is. And that's the joy of having a living, improving product. So that's it for our demo, yeah?
Yes, I think so.
All right. Well, thank you very much for joining me. Is there any tricks or snags or anything else that you think people should be aware of with this that may be worth keeping in mind while they go get their hands on this and start testing it right now?
I always like reminding people, use ST covers, not ST contains. That has historical reasons. That's the way these functions were called before. If you read the documentation about what ST contains does, you will be confused. and then you check the documentation for SD covers, and you say, yes, this is what I want. And SD contains is actually going to be a bit more expensive to compute than SD covers.
So if it's easier and cheaper, it's kind of a win-win, right?
Exactly.
I haven't seen any comments coming in from live stream audience. I think most people tend to watch videos after the fact. But if you do have questions and you're watching this wherever you may be at whatever time you may be, feel free to comment on LinkedIn or on YouTube. We will see it and we will get a response to you. And actually, we have a question from Ishank, which is, do we have different pricing tier or licensing structure for geospatial features, or is it included in the standard Firebolt offering?
Yeah, so geospatial capabilities are a part of our standard offering. There's no additional cost to using this. You can, if you're using Firebolt today, you can use it right away.
Yeah, so this is live in Firebolt. We don't have different tiers yet. That's also something coming. But when we do have different tiers, this will be included in all of them. So I think functionality is supposed to remain the same, and what separates standard from enterprise is different from this. So maybe that's a different LinkedIn Live.
Exactly, yeah.
In any case, thank you, Demian, for joining me today and explaining all of this. Thank you for the demo. Thank you to everyone who watched and tuned in. And I think that's it from both of us. So we'll see you next time.
Bye.